Okay, so we can get started with problem 3.7 from Wald's General Relativity here. He says that as shown in problem 2, an arbitrary Lorentz metric on a two-dimensional manifold locally can always be put into this form shown here, where we have essentially a flat space metric or flat space-time metric in 2 dimensions, or 1 plus 1 dimensions, whatever you prefer, and then it has this omega function factored out, but multiplying both terms. So he wants us to calculate the Riemann curvature tensor of this metric using the coordinate basis methods in section 3.4a and the tetrad methods from section 3.4b. So we can go ahead and do that. And I've already written here just the line element again in my own handwriting, and then with that the matrix in the metric in matrix form, just because I find this easier to look at. So because g mu nu is diagonal, we know then that trivially inverse g mu nu, we can just invert the components here, and we have a nice simple expression for that as well. Okay, so we're in 2D clearly, which we can see by our line element and metric and things, and it's also stated in the problem. So we'll say in 2D, so by problem 3. So hopefully you guys have done problem 3 from this chapter. If you have, you'll know there's only one independent component in 2 dimensions. Only one independent component. So we can pick what we want here. We're just going to take 2b r1 2 1 2, and everything else essentially follows from this by symmetries. So we can use our equation up here and essentially just write explicitly a form for this term of the Riemann tensor. So note that we know what mu, nu, rho, and sigma are because we've picked a component that we're going to do this for. So for those indices, we can just fill them straight in, and then anything left over might have to be summed over or something like this. But the first step I'm going to do here is basically just rewrite this with all these replaced with the 1s and 2s that we've decided to use. So that's going to look like this. R1 2 1 2 equals, let's see, so d2, or the derivative with respect to the second coordinate, times gamma 2 2 1 minus derivative with respect to the first coordinate, gamma 2 2 1 plus gamma. So we have now an alpha here that's going to be a dummy index that's summed over because it's not specified. 2 alpha 2 minus gamma alpha 2 1 gamma 2 alpha 1. So we can explicitly do the summing of the dummy indices and rewrite this. So let's go ahead and do that. Okay, so we're going to have a first term where alpha is 1. Another term when alpha is 2. Now we move on to this last term, first one being with alpha as 1. Oops. My writing's so messy right now. So what are we doing? We're doing this with gamma as 1 right now, and then we're going to have one more subtracted off where alpha is 2 instead. If I said gamma is 1, that is not what I meant. I meant alpha is 1 and 2 here. Okay, so that is our complete expression, and so this is going to tell us which of the Christoffel components we actually need to calculate. So let's see. We need 2 2 1. This is the same thing. 2 1 2, but that's just 2 2 1 backwards. But okay, so gamma 1, 1, 1 we will need. 2, 1, 1, 2, 2, 2. 2, 1, 1 we already have. 2, 2, 1 we already have. Okay, so these are the components that we need. So as the next step, we can just go ahead and start calculating these. So I'm not going to pull up the equation explicitly again, it's in one of the previous problems. But instead we can just write this stuff out pretty quickly here. So let's see, first we're going to go gamma, let's say 2, 1, 1, is 1/2 g 2, 2 dg 1, 2 by dx1 plus dg 1, 2 by dx1 minus dg 1, 1 by dx2. So we know that g is diagonal, so automatically these terms go away. So we get 1/2, and then g22 with the indices upstairs, so that's going to be 1 over omega squared. And then we get negative the derivative of g11 with respect to x2. So g11 is going to be minus omega squared. So it's d2 minus omega squared. Okay, so we can go ahead and pull the minus sign out, make it positive, so we end up with something like 1/2 1 over omega squared d2 of omega squared. Now we can actually take this derivative and simplify things further, so this is 1/2 1 over omega squared, times 2 omega d2 omega, just by chain rule. So we're going to have some cancellations here. The 2's cancel, this omega cancels with the square in the denominator, and we end up with something like d2 omega over omega for this Christoffel symbol. Okay, so carrying on, let's calculate gamma 2, 2, 1. So similarly, we get the 1/2 inverse g22 out here, and then, okay, so I'm just going to write the inside of the brackets. And we can have a look at this now. So the off diagonal components obviously are going to go away like always. So we get 1/2. This g22, if I remember correctly, is 1 over omega squared. Maybe there's a minus sign. There's not a minus sign. 1 over omega squared. And then we get the derivative of g22 with respect to the first coordinate. So let's see, g22 is what again? Minus omega squared? No, just omega squared. Okay, so once again, we can actually do this derivative and simplify a little bit. So we get 2 times omega times d1 on omega. Get some cancellation with the 2's and the square, and we get that this is d1 omega over omega. Okay, carrying on, I can calculate this one next. With 1, 1, and 1. So this is 1/2 inverse G11 times del G11 by del X1 plus del G11 by del X1 minus del G11 by del X1. So at first glance, it looks like there's going to be a lot contributing here because these aren't off diagonals, but these ones actually just cancel with one another because they're the same. So we end up with 1/2 inverse G11 is going to be minus 1 over omega squared. And then we get d1 of G11, which is what? Minus omega squared. Okay, so as before, now we can pull out the minus sign. This is simply just 1 over 2 omega squared d1 omega squared. So let's do the chain rule here. So we get 1 over 2 omega squared times 2 omega d1 omega. So the 2's cancel, the omega cancels with the square, and we get something similar again. I'll write it down here though. So gamma 1, 1, 1 is del 1 omega over omega. So you start to notice a trend here. These all look pretty similar. Okay, I think we got 2 more to calculate. So 2, 2, 2 now. It's going to be 1/2 G22. And then for similar reasons to the last one, we get cancellation on the last 2 terms. So I'm just going to write this first one. Get something like that. So this is going to be 1/2 1 over omega squared d1 omega squared. So very similar to what we've already seen here. The chain rule gives us a 2 omega d1 omega. 2's cancel, omega cancels with that square, and we find that 2, 2, 2 is d1 omega over omega. I made a mistake here. That shouldn't be d1, it should be d2. For obvious reasons. And then, okay, we have one more component to calculate here. We get gamma 1, 2, 1 equals 1/2 G11 dG11 by dx2 plus dG21 by dx1 minus dg21 by dx1. Okay, so the off diagonals go away. G11 upstairs is minus 1 over omega squared. Now we get a d2 of minus omega squared. So the negatives are going to cancel because we can pull them out. This is going to be something like 1/2 1 over omega squared times, if we do the chain rule, we get 2 omega d2 omega. Cancel, 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 cancel. 1, 2, 1, and we get d2 omega over omega. And that's it for the Christoffel symbols. So we can remember now that our 1, 2, 1, 2 equals del 2 gamma 2, 1, 1 minus del 1 gamma 2, 1, 2 plus gamma 1, 1, 1 gamma 2, 1, 2 plus gamma 2, 1, 1 gamma 2, 2, 2 minus gamma 1, 2, 1 gamma 2, 1, 1 minus gamma 2, 2, 1 gamma 2, 2, 1. Okay, and we can just start plugging things in basically. So let's see, we have, so let's plug in gamma 2, 1, 1 here. It's d2 omega over omega. Minus d1 of gamma 2, 1, 2, which is going to be the same as gamma 2, 2, 1, which is this, so delta 1 omega over omega. Plus, okay, gamma 1, 1, 1. It's delta 1 omega over omega. And then 2, 2, 2 is going to be delta 2 omega over omega. Oh, hold on a sec. I got confused here. This is wrong. So we have 1, 1, 1, which is this, and then 2, 1, 2 is supposed to be the next one, which is going to be the same as this, which is a delta 1 omega over omega. Okay. Okay, so that's term 1 dealt with here, term 1 of the just Christoffel symbols. So I'll move on to the next one now. Gamma 2, 1, 1 is, we've already used that once. It's 1 over omega d2 omega. So let's do that. And then 2, 2, 2 we haven't used yet, but I do remember what that is actually. It's del 2 omega over omega. Now we still have these last two terms to deal with. So 1, 2, 1, have we used that yet? No, so let's look at 1, 2, 1. And 1, 2, 1 is del 2 omega over omega. And then 2, 1, 1, which we have used, it's del 2 omega over omega. And finally, one last term here. So 2, 2, 1 is the same as 2, 1, 2, which we used already. So it's 1 over omega delta 1 omega. And then we have, oh, the same thing again. Okay, so right away we can see that this term cancels with this term, and this term cancels with this term. And what we're left with is just these first two with the derivatives. So there's a number of ways to do this, but what we can think about is actually rewriting these terms in the brackets in terms of a natural logarithm. So this is actually equal to d2 of ln omega, if you think about it, because this will give you 1 over omega times d2 of omega. So let's actually rewrite our Riemann tensor now. to be like this. I'm going to get del 2 of del 2 ln omega minus del 1, and we're going to make a similar substitution here, del 1 ln omega. And what this actually means is we get minus del 1 squared plus del 2 squared acting on ln omega. So we're almost there now. If we want to think about this in a lowered form though, so excuse me. So for comparison later, it'll be easier if we lower it. We're going to want our 1, 2, 1, 2, and this is going to simply be something like G 2, 2 times R 1, 2, 1, 2. And since we know G2, 2 is just that omega squared, finally we get that this is omega squared minus del t squared plus del x squared ln omega. Okay, so we can try part B now, where we do this instead with the tetrad methods of section 3.4b. So let's just remind ourselves of our line element. Where omega is a function of both t and x. So the idea here is that we'd like to introduce a non-holonomic orthonormal basis satisfying So the kind of trivialist or most obvious way of approaching this, I guess, is to set these e's up this way. So say e mu a is going to be some constant alpha times the muth coordinate, and we take the 8th component of this. So this is kind of a weird notation, and I'm still not fully used to this, but basically what Wald means by this, if you have like d by dta, for instance, this just means a vector that in the coordinate system that we're working in is 1 in the time slot and 0 in all other slots, essentially. So if instead of a t down here we have like a x2, then it's just like this gives 1 when a is 2, essentially. So this means then that E1a is going to be alpha d by dt a, and E2a is going to be beta, some other constant, d by dx a, because t is the 1th component and x is the 2th component, we'll say. Okay, so what would lowering these a's look like if we want to consider E1b, for example? This is going to be GAB times E1a upstairs. Now, remember that only when a is 1 is this going to be non-zero, because of this property of what the E1s are. So let's say we actually get G11, E1, 1. And so that's going to give us, let's see, minus omega squared for the G11. And then E1a is going to give us alpha. Now, since we're lowering this, let me think. Yeah, this becomes, instead of being d by dt for E1, because we're lowering the index, it becomes a dt. This is just a notation thing with the b down there. Okay, so similarly for E2, we would lower it with the metric. So similarly, we get an omega squared out front here from the metric term, and get a beta dx with a lower b. And now we can figure out what alpha and beta actually should be by using this property here. We know that, let's say E1A, E1A is supposed to equal A to 1, 1, for instance. So this gives us GAB times E1A, E1B. Now we know that actually GAB can be written as omega squared times A to AB. So let's do that. And then take these E1As and E1Bs, and essentially what these E1As and E1Bs are going to give us is each an alpha, and then a delta, just saying that A has to be 1 and B has to be 1. So if we evaluate those deltas, we get something like omega squared, alpha squared, A to 1, 1. So then this implies that alpha is 1 over omega in order for this property to be satisfied. We can do the same thing for beta. So for beta, we'll just think about E2 instead here. So write down E2A equals, remember we would just raise and lower things with the metric, so we can put a GAB here and get E1A, sorry, this should be E2A, E2B. So again, we can write the metric as omega squared times eta squared, or not eta squared, but times eta, AB. And then we're going to get a beta squared out of these E2s, and then two deltas, A2 and B2. So evaluating those deltas, we find this implies that beta is also 1 over omega, which is the same as alpha. Okay, so we've set up our basis, and I mean, we didn't really have to go through all this. We could have just guessed that this was the correct choice, but I'd just like to show things for my own sake. So there we are. That's what we're working with. And so let's just kind of clean everything up, and let's show what we have so far. So we know that E1A is 1 over omega d by dt A E2 A is 1 over omega d by dx A, and then we can also write down what they look like when they're lowered. So this is going to be E1. I'll write it as B. It's going to be omega, let me think. E1 is going to be minus omega squared times alpha. So we end up with a negative omega times dtb, and E2b very similar. We just get omega dx b. So here's what we're working with. Let's do that a little better. So now, let's start working towards the Riemann tensor. So we'll write down this equation, 3.4.21, where we know that R rho sigma mu nu is E rho A nabla A omega sigma mu nu minus E sigma A nabla A omega rho mu nu minus eta alpha beta, oops, I did not do that good, alpha beta omega rho beta mu omega sigma alpha nu. We're going to have to continue over here, minus omega sigma beta mu omega rho alpha nu plus omega rho beta sigma omega alpha mu nu minus omega sigma beta rho omega alpha mu nu. Okay, so that's quite an expression, but that is okay. It's a lot of plug and chug, honestly. So remember from part A that we've decided that, well, not decided, but in 2D, there's only one non-trivial component to the Riemann tensor, and what we've decided is that we're going to look at component 1, 2, 1, 2. So let's look at this. 1, 2, 1, 2, and we're going to just fill in the 1s and 2s where appropriate in the above expression. So we get E1 A nabla A W212 minus E2 A nabla A W112 minus eta alpha beta omega 1 beta 1 omega 2 alpha 2 minus omega 2 beta 1 omega 1 alpha 2 plus omega 1 beta 2 omega alpha 1 2, and finally minus omega 2 beta 1 omega alpha 1 2. Okay, so let's rewrite this once again, but this time expanding out the eta alpha beta, and summing over the alphas and betas here. So, okay, this is going to be equal to E1A 212 minus E2 A nabla A W112 minus, okay, so we're going to pass the eta through here, and so we're going to start with an eta 1 1 omega 1, 1, 1, omega 2, 1, 2, plus omega 2, 2. So we're only going to be using the diagonal components because eta is diagonal. And then this is going to be omega 1, 2, 1, omega 2, 2, 2. Let's see. Minus eta 1, 1 on omega 2, 1, 1, omega 1, 1, 2. Minus eta 2, 2, omega 2, 2, 1, omega 1, 2, 2, plus eta 1, 1, omega 1, 1, 2, omega 1, 1, 2, plus eta 1, 2, no, sorry, 2, 2, omega 1, 2, 2, omega 2, 1, 2, minus eta 1, 1, we're on the last term here now, omega 2, 1, 1, w 1, 1, 2, or omega, whatever, I think I'm using them interchangeably at this point, minus eta 2, 2, omega 2, 2, 1, omega 2, 1, 2. Okay. So one thing we know about these omegas, the connection one forms, is that they are antisymmetric in the last two indices. So let's write this up here. WABC equals minus WACB. Therefore, WABB equals 0 trivially. So with that, this goes to 0. 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 And we're left with not so many terms anymore. So let's remind ourselves as well that eta 1, 1 is negative 1. Eta 2, 2 is 1. And let's rewrite what we have here. So we get E1, A, nabla, A, omega 2, 1, 2, minus E2, A, nabla, A, omega 1, 1, 2, minus, okay, so we get put a bracket, and we actually get from this term a negative, oh wait, this should be 0 because it has a 1, 1 in it, yeah. So actually, this are gonna be our first term. So we get a minus 1 times the square of omega 1, 2, 1, 1, 2. And then we get minus w2 or omega 2, 2, 1, omega 2, 1, 2. So actually, because of the antisymmetry property as well, we can rewrite the brackets like this. Minus omega 1, 1, 2 squared plus omega 2, 1, 2 squared. So all in for our 1, 2, 1, 2, we get something like this, which doesn't look so bad anymore. Okay, so now it remains to calculate the omegas that we're going to use. One thing we can say is that the omegas are a scalar. So I'd like to write that a little better, which means that our covariant derivatives can become normal derivatives. So I'll just write that down to remember, but also to calculate use this equation right out of Wald. I can't remember what the equation number is for this, but it's in that section. Okay, so let's just go ahead and expand the anti-symmetry brackets. Makes it easier to work with, in my opinion. So let's look at it like this. We get 1/2 del A E sigma B minus del B E sigma A equals 1/2 eta mu nu E mu A omega B sigma nu minus E mu B W A sigma nu. Okay, so again we can expand and do the sum for the right hand side. So let's do that. This equals, well, first let's cancel the 1/2 because those are just gonna get in the way. And then we get something like this. Let's say eta 1/1 times E1 A omega B sigma 1 minus E1 B omega A sigma 1 plus eta 2 let's see, E2A omega B sigma 2 minus E2B omega A sigma 2 and then at the end of the day we can just plug in these values for eta and we get a right hand side like this. We get E1B, so I'm just using the fact that eta 1/1 is a minus sign and flipping these brackets. Get omega A sigma 1 minus E1 A omega B sigma 1 plus E2 A omega B sigma 2 minus E2 B omega A sigma 2. So we can consider cases now to think about how this is going to work out. So let's consider first sigma equals 1. So with that, we can rewrite everything here. So the left-hand side ends up becoming this. So this is right away going to be 0 because the last two indices of the omega are the same. E1 A omega B11 for the same reason, this just goes to 0. Plus, let's see, E2 A W B12. This one isn't trivially 0. Minus E2 B omega A12. So we're going to let A equal 1, B equal 2. And with that, we get this del 1 E1 2 minus del 2 E1 1 equals E2 1 omega 2 1 2 minus E2 2 omega 1 1 2. So effectively what this is then is del 1 of 0, so that's going to go away, minus del 2 of minus omega and this is going to equal 0 times W212 minus omega times W112. And the reason that like these E11s, I'm not bringing in the derivative term is because once both of these are specified, we get a 1 and a 1. It's just a delta that lets 1 equal 1, basically. It sets the indices to be the same, or gives a 0. So yeah, that's where that's going here. So we can continue to simplify. The derivative of the 0 term just goes away. These minuses are going to cancel with each other, so we just get del 2 of omega on the left side. Equals a 0 term, we say minus omega W112. So this implies then that W112 is minus del 2 omega over omega, and we're going to make use of a little trick here. So recalling the fact that the derivative of the natural log of some function is going to be 1 over that function times the derivative of the function itself. Because of this, if we look at the right-hand side of what our W112 is, it looks a lot like a natural log. So we can actually rewrite and say that this W112 is minus del 2 minus del 2 of the natural log of omega. Okay, so we can do the same thing, but for sigma equals 2 now, which means we'll be taking this equation and this left-hand side and this right-hand side and replacing the sigmas with 2. So easy enough, we can go ahead and do that. So we're going to get on the left-hand side del A of E2B minus del B of E2A equals E1B WA21 minus E1A WB21 plus, and we get E2A WB22, oops, minus E2B WA22. Now, if we recall the antisymmetry property of these W's, we know that WABC is the negative of WACB. And because of that, a direct consequence is that WABB of any kind has to equal 0. It's the only number that's going to be its own negative. So for that reason, this goes to 0, this goes to 0. And now we can set A and B how we like. We're going to just do it the same as last time. So let A equals 1, B equals 2. And we rewrite. So del 1 E2 2 minus del 2 E2 1 equals E1 2. Let's put a big bracket here. W1 21 minus E1 1 W2 21. So that is going to be then del 1 of omega minus del 2 of just 0. Get a Kronecker delta of 2 and 1, so it's going to be 0. Again, we get 0 here for a similar reason, times W121 minus, and then we get a negative omega in the bracket, and W221. So with this, it's relatively straightforward to see that we just get del 1 of omega is the 2 minuses cancel over here, omega W221. So this means that W221 is del 1 of omega over omega. And as before, we can use that natural log trick. So we're going to say W221 is del 1 of the natural log of omega. Okay, so we have these two W's now, but it's important to remember that what we've been calculating are WA, where is this? WA mu nu. And in the actual equation that we're going to use for the Riemann tensor, those W's are W lambda mu nu's. And so there's a relationship between these. We know that W lambda mu nu equals E lambda A W A mu nu, which are the ones that we already have. So right away here we can just go ahead and say like to get our W's in this form, we can say W112 in the form we have it is going to go to E1 1 W112 as we have it plus E1 2 W212 as we have it. But this E12 is just a delta that evaluates to 0, so let's let that go to 0. And so we actually find that our W112 goes to 1 over omega from that E, W112. And so what that actually means, let's see, our W112 is this, minus del 2 ln omega. So just going to remind myself here, minus del 2 ln omega, okay. So this is like what we're actually going to use in the equation for the Riemann tensor. Similarly for our other W, actually I'm going to outline this in a different color just so I don't get confused. Even more so, there we go. Okay, and then for the other one, we have W212, which is going to go to E2, I'm just not even writing down that first one, that's going to evaluate to 0. And we get W212 here, as we already have it. So with this, we get, again, a 1 over omega times W212 as we have it, which is just to the left here. So for W212, we're going to let it be in the Riemann equation 1 over omega times del 1 ln omega. Very similar to the other one. Okay, so we have those. And we have an equation for the Riemann tensor. I think. Yeah, right here. So let's go ahead and write this down again while letting those sums actually expand and see what happens now that we have these w's. So I can say r, oops, I don't want to keep working in that color. R1212 is E1, 1, del 1, W212 plus E1, 2, del 2, W212 minus E2, 1, del 1, W112 plus E2, 2, del 2, W112 plus W112 squared minus W212 squared. Okay, so we can actually, well, let's see. First of all, this E12 is going to go to 0 for obvious reasons, as is this one, E21. So what we really have here, we can rewrite this. The E11 is going to give us a 1 over omega del 1 W212 minus 1 over omega again del 2 W112 plus W112 minus W, oh, sorry, this is a square, minus W212 also squared. So let's substitute in these nice w's that we've derived now. So in doing so, we get something like this. I'm going to factor out a 1 over omega. Get del 1 of, let's say, minus 1 over omega del 1 ln omega. Let me just make sure that's right. 212. Oh, I switched. Two, 1. Oh, there should be a minus sign here if we're doing it in terms of 2 and 2. Okay. So this will be minus because W212 is minus del 1 ln omega because the anti-symmetry property. And 2 and 2 is what we actually end up working with. Yes, so this, what I've written down is correct, but yeah, it's important to remember the minus sign. Okay, and then we get minus, the 1 over omega is already taken care of, so we get del 2 omega 112. So again, minus 1 over omega, it's going to be a del 2 instead. Okay, so minus 1 over omega del 2, sorry, ln omega. And then this is going to be 1 over omega squared minus del 2 ln omega squared minus 1 over omega squared. Again, we're just punching in for these w's here. Minus del 1 ln omega squared. Okay, so now we can start by doing a little product rule action in here. Actually first, before we do that, let's make life a little bit easier by just distributing some minus signs. So it's 1 over omega minus del 1, 1 over omega del 1 ln omega plus del 2, 1 over omega del 2 ln omega plus, and then we're just going to write the rest of this as dot 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 for now. We'll come back to it. So now we can start the product rule. So a minus, and then let's just open a bracket here. So we're going to have del 1 of omega to the minus 1 times del 1 of ln omega plus omega to the minus 1 del 1 ln omega. And then for the next term, we get del 2 on omega to the minus 1 del 2 ln omega plus omega to the minus 1 del 2, oh actually, yeah, del 2 squared ln omega. And this del 1 here should also be squared in that term. Okay. And then we, of course, have our close bracket and our plus dot 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 here. Okay, and we can continue going with this. So keep our 1 over omega here. Now, the derivative of this is going to be minus omega to the minus 2 times del 1 omega del 1 ln omega plus omega to the minus 1 del 1 squared ln omega plus, so same thing here, minus omega to the minus 2 del 2 omega del 2 ln omega plus omega to the minus 1 del 2 squared ln omega. Oops, that last omega is a mess. Plus our dot dot dot. Okay, now if we write these a little bit differently, I'll do that and distribute some minus signs. Our natural log trick is going to kind of come back here. So, okay, distribute this minus sign, we get 1 over omega, 1 over omega, I'm just writing them separately now, del 1 omega, del 1 ln omega, minus, let's write it this way, del 1 squared ln omega over omega, minus 1 over omega, 1 over omega, del 2 omega, del 2 ln omega, plus del 2 squared ln omega over omega, and then everything else. Now the reason I wrote it like this with the omega to the minus 2 kind of being split into separate ones is so that you can see that this here is simply just using that trick again. It's just del 1 ln omega, and that's same with here but with a del 2, and that allows us to rewrite this in a very convenient way. So let's go ahead and do that. We get 1 over omega times del 1 ln omega, and this is squared, minus del 1 squared ln omega over omega, minus 1 over omega d 2 ln omega squared from that same trick. del 2 squared ln omega over omega. And now, okay, let's write the rest of what we've been dropping now. So we have a plus 1 over omega squared. The minus sign inside here isn't going to matter because it's being squared, so get del 2 ln omega squared, basically, minus 1 over omega squared. And same thing, the minus sign goes away, and we get del 1 ln omega squared. Now, it should be obvious, but I'll just point this out, that there is a difference between these del 1 ln omega with the square on the outside and these del 1 squared ln omegas, because this del 1 squared is saying that the del 1 operator is being applied twice to the ln omega, whereas here we're taking del of the ln omega and squaring the result. So yeah, keep in mind that those are different. But we'll also notice here that we have a del 2 ln omega with a plus sign, or del 2 ln omega squared with a plus sign over omega squared, and oh, I have a sign error somewhere. Oh, no, I don't. I was just looking at the wrong thing. Okay, so this is going to cancel with this, and the reason is because we have a 1 over omega out front, so we're going to have a 1 over omega squared, and then del 2 ln omega all squared, this one with the minus sign, this one with the plus sign, so that's good. Similarly, this is going to cancel with this, and we're left simply with minus del 1 squared ln omega over omega plus del 2 squared ln omega over omega. So we can simplify this a little bit further. Let's remember what we're calculating to. So this is our 1, 2, 1, 2 equals, and we're going to say 1 over omega squared minus del 1 squared plus del 2 squared acting on ln omega. So that's good. The last thing to do is relate this back to the Riemann tensor we calculated, or the Riemann tensor component, sorry, that we calculated using the component methods. So these are related like this. This can be found in the book, but I will write it here. R A, B, C, D equals R mu nu sigma rho E A mu E B nu E C sigma E D rho. And so essentially the one on the left-hand side is the Riemann tensor component above that we've calculated with the tetrad method, and on the right-hand side is the coordinate Riemann tensor. So let's just make sure that they agree if we punch them in. So for us, we have our 1, 2, 1, 2 from the tetrad method, we'll call it, on the left-hand side equals our 1, 2, 1, 2 from the coordinate method times E1, 1, E2, 2, E1, 1, E2, 2. So each of these is going to give a 1 over omega. So at the end of the day, what we get is on the left-hand side, we get omega to the minus 2 minus del 1 squared plus del 2 squared ln omega. And this is going to equal, let's put this in brackets because this is our tetrad Riemann tensor component, Our coordinate one is going to be here. It's going to be omega squared minus del 1 squared plus del 2 squared ln omega, and then each of these e's is going to contribute to 1 over omega, so we actually get an omega to the minus 4 out front here. And so the effect of this is that this omega cancels with this 4, making it a minus 2, and both sides are indeed equal at that point. So we know that we've done it right and that they agree.